Hi, so this is a question about something that one of you sent me, and I thought it would be best to try and make a small video about this so that I can explain myself a bit better. What happened before is that I went through this a little too quickly, and hence it was not, appropriate for me to do that. So you would remember that when we had looked at uh, when we were looking at special theory of relativity and electromagnetism, we discussed something which was the electromagnetic field tensor that was given by F mu nu, which is of the circle form. When we wrote this down in the matrix form, this F mu nu downstairs, this became this matrix here. Now, so what one of you were asking me, and this is a very valid thing to do, is when I wrote F mu nu down with these two etas, written in the form that it is here, it would just look at it, it would just seem that, F mu nu is like this eta, which is 1 minus 1 minus 1 minus 1, and another 1 minus 1 minus 1 minus 1 into this F, which is with indices downstairs. So if you multiply this 1 minus 1 minus 1 minus 1, two of these, this would just become identity, and so hence F mu nu upstairs and F mu nu downstairs, they should be the same. And why do I have these sign flips between the two? This was a very valid thing to ask. And what I should have mentioned, so the placing of these matrices are actually very crucial. So actually what you need to do, you need to place one eta in front of the F and one eta behind the F, and thereby you get the right signs. So the answer, of course, was right, but what I should have stressed on this more. So instead, so let me try and run you guys through an example of a little bit of a simplified case where I just clearly mention all of this. So we will start off with the three-dimensional version of F mu nu given here. So you see that we just have Ex, Ey, and Bz. So there is a sign which is off. I think this is going to be a minus Bz, but okay. So you'll get the hang of it. So I don't want to. This is actually a minus. So sorry about that. So I'll just quickly change a couple of things. All right. So what I wanted to ask you, what I wanted to clarify is this F mu nu, and we are looking at the three-dimensional version. So you have Ex, Ey, and Bz, and your eta now has three entries. Now, as I said before, F upstairs and F downstairs are related by two etas. But the important thing here to notice is what is the index structure. So remember that when you have a matrix CAB and you want to write this in a certain if you want to write this in terms of, so okay, let's just C, matrix C is, say, A and B in matrix notation. So when you write this down, C, if you wish, Ij, this has to be, so let me make sure that so let's say that this is A into B into D, okay? So this has to be written in a form which is AI K B KL and DLJ. So you notice, of course, there is going to be a sum over K and L, as you know. But the point what I'm trying to make is that these indices have to be in a way such that the summed indices have to follow each other, in the sense it has to be AIK and BKL and DLJ. All right. So if you could have of course written this as AIK, BLJ and DLG and BKL when you write it in this particular tensorial form, but you'll have to remember to bring it in the right order when you are looking at this in trying to in the matrix form. Okay, that is what is the main point here. Okay, so if you do this, so if you are looking at this equation now, it means that the structure that you have written out here is not in a form that we can directly, so you can't write this particular thing that you have out here. This is not F cell tilde equal to eta into F. Okay, this is not true as a matrix equation. So let's just so it matters where you are going to put the matrices. Okay, as I said, you have to put it in a way such that these repeaters indices sit side by side. So this has to be brought to a form like this. Okay, so how do you do this? You notice that you had something which is F rho sigma, which is equal to eta mu nu, eta rho nu, F mu nu. Repeated indices have to come side by side. So this would mean that F mu nu is here. Now you also have eta sigma nu. Now you have to make this, you have to change this into something. So this, if you change this, in our case it's a symmetric thing, it doesn't matter. So you can flip things around. F mu nu into eta nu sigma. But in a sense, this is just a transpose of the matrix eta. So the proper way to write this is F tilde. I'll just call the upstairs indices with this tilde here, is eta F eta transpose, because you see this is a mu, this is a nu in nu sigma on top, and you have to and you started off with sigma nu. So you need to flip this around as well. So that's why you get this transpose here. In this case, it doesn't really matter, because so what you will, so this is diagonal matrix. So the transpose will obviously be equal to itself. Now if you write this down, and now if you write down 1 minus 1 minus 1 and the matrix F and 1 minus 1 minus 1, of course, the two 1 minus 1 minus 1s don't sit next to each other. They don't give you identity. And you can just do the matrix multiplication and see what we actually did earlier was all right. But it's important to stress this. And this is in a sense, this is why, in some sense, that tensorial notation is simpler, because you can actually disregard all of this and just move things around. As we saw when we were doing this explicitly later, if we just put these, if you want to look at the transformations, you can just put these the values of mu and nu, the indices in, and you can get the answers out of that. But I just wanted to stress that this was a very important point, and then this is why I thought I would just create something short for you explaining this. I hope that was more helpful. If not, please feel free to write to me again. Thank you.